Hi, my name is Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So is everyone awake after their lunch today? Can I see anyone asleep out there? There's one over there. Okay, so I want to thank the organizers of ICCF22 for inviting me to present Alexander's work. Alexander unfortunately couldn't come. His doctor advised him to not get or do anything that's too exciting. So I know you're all excited. But anyway, so yes, the nickel hydrogen heat generator continuously working for 7 months. So this data was available just before ICCF21, but the analysis of the reactants hadn't been done, and so it's better that it's presented here to give a better picture. So, the peculiarity of this reactor is that it stopped working, not because of the burnout of the heater, as it was until now with all of its other previous reactors, but in the process of smooth reduction of excess heat as a result of the depletion of the energy resource of the fuel. In total, 4.2 gigajoules of excess energy was produced, more than 2 MeV per 1 atom of nickel. The maximum excess power is 1,020 watts, COP 3.6, and the average excess power is about 220 watts, average COP 1.6. The reactor operated for 225 days, and the fuel was PNKO-T2 nickel. Now, we analyzed this in many locations. It was sent to many labs, and this is Bob Higgins' stereographic image, which is just off the shot there. I think I'm going to lose a lot of titles, but anyway, sorry about that. So if you blur your eyes and squint in the middle, you might see it in 3D. This is fun. Okay, so the preliminary operations, and if you want to know really what you should do with any material that you want to occlude hydrogen with, you need to go back to Thomas Graham FRS from 1867, who defined what you needed to do. And essentially it is, as Piantelli says, you need to absolutely clean the surface of nitrides and oxides. And in his paper accompanying this, he describes the process here. And essentially it's a case of loading it below the sinter temperature of these wonderful structures you see here. And you need to sort of pump in and pump out with hydrogen for a number of cycles and reduce the oxides and so forth, and leave it to soak for a period of time for 3 days at temperature of 350 degrees C. Then after then after repeating the pumping cycle twice more, he filled the reactor. And heat generator was moved from the preliminary preparation area stand to the main workstation. So this is the components of the reactor before it ran. These are silicon bungs that go into the end. These are, as I found out, silicon dioxide foam here as well, and this separates the various components, and there's some things that you don't see in here that which we'll see when it's broken up at the end, and we will move forward. Okay, so okay. Hello. Okay, so the heater pipe was comprised of a tungsten wire, and the reason it's in this area here is that tungsten starts to oxidize, 800 or 1,000 degrees C, so this is a hydrogen atmosphere in this whole area here. And it's spiral wound an aluminum tube. It has to have a lot of coils because it's got a low resistance. Between the fuel pipe and the heater pipe was a junction of tungsten rhenium thermocouple, so that's this point here. A chrome aluminum thermocouple was monitoring the temperature on the outside. Here, heat resistant silicon dioxide felt washers, as I just described, are here, and the other side, as in the mirror. And the ends of the 50% alumina and 50% mainly silicon dioxide outer tube are insulated from the atmosphere with silicon sealant here and here. And a metal tube comes from the ends of the reactor to connect to the manometer here. I'm going to skip over this, but basically the secondary winding has a 630 watt capacity. He switches between power. The volts and amps are measured here. He has a thermometer on the inside, a thermometer control on the outside with a TPM 500, pressure gauge, and a Geiger-Muller counter, and it's all computer controlled and recorded. He has a power monitor here. This is the actual setup you see with the ammeters and voltmeters and so forth. You've got a power watt meter down here, and this is a temperature controller, Variac, and so forth. You can look at this in your own time, and it's in the paper. Okay, this is where I have to get detailed. So, during the first day, the electric current heating power gradually increased, which was accompanied by a smooth increase in the temperature inside the heat generator to a temperature of about 1,100 degrees C at a power consumption of 400 watts. Further increase of power up to 700 watts led to heating up to 1,500 degrees C and the appearance of heat generation in excess of consumed electric power of about 130 watts. After reduction of the electric heating capacity to the previous level, the excess heat generation capacity after decreased to 80 watts, and the ratio of heat generating capacity to electric power consumption, COP, remained at the level of 1.2. The methodology for determining the excess capacity will be discussed later. Subsequently, at the constant power consumption over 18 hours, the temperature inside the reactor increased from 1200 to 1500 degrees centigrade, and the COP changed from 1.2 to 2.3. An increase in electric heating power up to 700 watts led to a short rise in temperature to 1800 watts, and an increase in COP to 2.7. But after that, the same power of electric heating, the temperature and the COP decreased sharply. After about 2 hours, the temperature returned to its previous value of 1800 degrees C, and such a high temperature was maintained even after the electric heater power was reduced to 400 watts. At the same time, the power of excess heat generation exceeded 1000 watts, so that's where this 1020 watt comes from, and the COP value reached 3.6. Such high values persisted for about 6 hours, then the decline began, and a day later, at a constant power of electric heating, the temperature dropped to 1300 degrees C, and the excess up to 200 watts. So is everyone following what I'm saying? Read it later. Okay, so in this one, thank you, Ruby. Further operation of the heat generator from 14th of October to 23rd of May 2018 took place in electric heating power that varied from 350 watts to 380 watts. So what he's talking about here is this sort of wibbly power here. That's due to some fluctuations in the domestic power supply, I guess. These controlling the exception was a few short-term increases in heating power. These control increases, except for the last one on May the 17th, where's the 17th of May? Somewhere over here. Oh, no, I've gone forward. Now I've lost it. Led to an increase in the temperature and COP. An increase in power on May the 17th also led to an increase in temperature, but the COP value remained close to 1, which indicated that the resource of the heat generator was exhausted. So they tried to increase some power here, but it went down to a COP of 1. So that's basically it's died. Despite the fact that the electric heating power varied within small limits, the parameters characterizing the operation of the heat generator changed significantly. A gradual spontaneous decrease in temperature inside the heat generator and excessive heat production, which lasted until October the 13th, was replaced by growth that lasted until October the 18th. The temperature increased reached 1550 degrees C. The power of the excess heat increased to 550 watts, COP of 2.5. After this, there was again a decline, followed by a gradual increase, which continued until mid-December. From mid-December to mid-March, the temperature inside the reactor varied between 1300 and 1400 degrees C, and the power of the excess heat gradually decreased from 300 watts to 200 watts, and the COP value decreased from 1.9 to 1.5. Okay, this is all in the paper, and you can follow it through, and every single part of the chart that you need to look at is in there also. So, hydrogen pressure. The initial pressure was close to atmospheric. During initial heating days, it went to nearly 1 bar overpressure, which was vented to the atmosphere via a valve. From the third day onwards, pressure fell below atmospheric, stabilizing at 0.8 bar 2 months later. On March the 16th, hydrogen was added to the heat generator to a pressure close to atmospheric. So he did add some hydrogen. This led to a slight increase in temperature and excess heat. The COP value increased from 1.5 to 1.7, but then excess heat power began to fall at an accelerating rate. An attempt to revive the heat generator on May the 8th by a second addition of hydrogen, he added hydrogen again, and an increase in the power of electric heating did not produce significant results. On May the 14th, the generation of heat, excess heat, ceased. So from my point of view, this is a really great experiment because I don't know many that have gone from nothing to excess heat for a very, very long period of time, back down to nothing. I think it's a very significant event in linear history. Okay, so heating power determination. Input power is easy to calculate from DC or low frequency AC with modern devices. Flow or evaporation calorimetry he considered to be impractical for an experiment of this length, 225 days. Curve fitting was used, starting with Stefan Boltzmann law, and was based on empirical data published during calibration with a resistive heater. Heating powers required to reach stable temperatures at a certain point in the device were recorded after the 20 to 30 minutes required to reach thermal equilibrium. Okay, so you can see here, he used the actual reactor. What he did was he ran it up to, from experience, he knows that he didn't get any excess heat below 1,000 degrees C. So the initial calibration was running the reactor up to 1,000 degrees C up here. It's not so clear on here, but these colors don't really stand out, but up to 1,000 degrees C. So they're the initial calibration curves. And he used that to form the polynomial curve here to predict the temperatures at higher regimes of input power. And then above the conformation and below were recorded after the fuel was exhausted. So what he did is when the excess heat of the reactor went to 0, he then used the exactly same device to see what the temperature would be as you put the power up, and also he also put the power down. So the post excess heat regime followed the same curve even in post calibration. So this is determining some excess heat. So measurements during operation before fuel was exhausted show no excess heat below 1,000 degrees. So these are measurements during the active run. So up to 1,000 degrees there's no excess heat, but as you go above 1,000 degrees it starts to deviate over here, and you determine your excess heat by the difference here. At higher temperatures the measurement results are located below the calibration curve, which indicates the presence of heat generation. This is the yield calculation, if you want to take a shot of that, because I don't believe anyone, so I do my own maths. So, this is the PowerPoint, moving things around. Okay, analysis of isotopic and element changes in fuel and structural materials. Essentially, there was no change in the nickel isotopes. Looked at Synthestech scientific research in Sochi and Uppsala University in Sweden, and that's the case for all of Alexander Parkhomov's reactors. They haven't observed nickel isotope change. However, Synthestech did see a lowering of 61 nickel ratio, but this wasn't confirmed at Uppsala. There was no changes in the tungsten. Oh dear, sorry about this. Analysis of the elemental composition of the samples taken from different places from the heat generator was made at Synthestech and Amterec LLC by energy dispersive X-ray fluorescence spectroscopy. And he observed a wide range of elements, both being synthesized in the bulk of the blob in the middle of the reactor and in the outer sort of central core of the reactor. So he was seeing vanadium, gallium, cobalt, strontium, ytterbium, hafnium. Now, I can say in the previous reactor, we actually, Alan Goldwater and I, in a university, Masaryk University, we tested this part, and this is from the 400 megajoule reactor. We tested this from the previous fuel, and we also observed gallium-69 in that by using moldy tough MS. So here's the mess afterwards, and there's all kinds of detail on what was where. But you can see here these two end pieces, and we were actually given one of these end pieces and a fragment of this. This is the central core, and this goes inside, and the tungsten rhenium thermocouple goes in between the two here and sits under this point. He had to crack this open. You can see where the wire was holding the thermocouple on the outside. But we actually have this bit. I have it here in my pocket, if anyone wants to have a look at it later. So we analyzed this at the Magic Sound Lab, courtesy of Alan Goldwater. And if you have samples that you need testing and you want to be open about it, Alan can provide a service at extremely reasonable rates, so you can understand what's going on in your reactor. But essentially, there's lots of things we found. Firstly, we found these fibers of carbon and also fluffy carbon. And so we're actually looking into some things that came out of the core, and also a big blob here. And in this blob, we found nickel, copper, tin, and lead. Obviously, we're going to see nickel. The interesting thing is there was silicon in large abundance. Also, you see calcium here, and a lot of carbon. So where's that carbon coming from? We also found these platelets. So this is the fluffy type of carbon, and these platelets, and they had iron, chrome, and calcium in them. This is another area. You can see these thin fibers, and these kind of fibers were observed being produced in Leclerc's cavitation experiments. Again, we've got chromium, iron, and calcium. I call this the pretzel. And we've seen these kind of structures in various experiments that we've looked at over the last couple of years, and it seems to be quite an important structure. On the backside, you can see this sphere at this point, which is, I think, at this point on the backside. It's actually physically quite large, and you can see these bands of fluffy carbon. And so we're seeing a lot of calcium silicon here, but it's the calcium, I think, that's interesting. So I did some calculations using the Alexander Parkhomov reaction table system that the MFMP has developed with Philip Power, and looking at starting with hydrogen isotopes and with a neutrino on the left here, we can end up with carbon. So I put this to Alexander Parkhomov. You know, you've got nickel, you've got hydrogen, you've supposedly got an alumina reactor here and some silicon dioxide felt bits. Where is all this massive amounts of carbon in fluffy and fiber things coming from? And this is the answer I got back. The large amount of silicon and carbon in the reactor is not surprising, since the inner tube, which nickel was located, consists of silicon carbide. Okay, so this is not disclosed until now. This material can withstand significantly higher temperatures than alumina. The inner tube is inserted into the alumina tube in which the tungsten wire heater is wound. The outer tube contains 50% alumina, the rest is mainly silicon dioxide. The heat insulating center washers consist, and that's where the detail comes from. So we've got some notes here, and the first one is, this is thermometry, and so you have the thermometer here. And Alan Goldwater discovered when we were doing the glow stick experiments, when we had a heater wire here and a heater wire here, and we had it on alumina, that if we had a thermocouple in the middle, what happened was, over 1,000 degrees, alumina, which this outer sheath is, we now know is, becomes a conductor. And this was the basis of the Nernst lamps, where you had a ceramic that becomes a conductor. And we found that we had leak currents, and could that explain the excess heat? But however, the effect could lead to leakage current artifact, but the fact that he used the same reactor with the input power ranges and saw the same temperatures down here and the same temperatures up here in post-calibration negate the potential of this. Second note is that silicon carbide is often doped with boron, and the XRF technology that they used wasn't able to detect boron, and he makes a point of it in his paper that it can only see aluminium. The interesting thing is, in the previous reactor, he actually suggested that the core actually had boron in it. And this is interesting because Alexander Shishkin is saying that string vortex solitons interact with boron, and we saw excess heat only when we had boron in our borosilicate glass when we were doing Celani replications, and there's boron in the center of a Piantelli reactor, and there's boron in some other reactors that people might like to admit in this room. Using the same reaction calculator, proposing that if there is boron in there, boron can go to neon, and then neon's confused to calcium. That is one way to explain the calcium, but of course tungsten can fission calcium as well, so maybe it's coming from that. This may be unlikely because of the way that these elements that have been synthesized have come from the inner tube and out. Thank you, nearly there. So the conclusion, optimization of the design, the use of more heat-resistant structural materials and reliable sealing made it possible to achieve a 7-month duration of operation of the nickel hydrogen heat generator with the excess power of a lot. During the process that took place in the heat generator, there were changes in the elemental composition, which I've been through, and significant changes in the isotopic composition of nickel as well as tungsten were not detected. And these are the people that Alexander would like to thank. If you have any questions, I'm ready to take them now.
G'day. You should be aware, and I am from unfortunate first-hand experience, that you take a tungsten rhenium thermocouple up to 1800 degrees, which was done early on, that when you have carbon around, you make tungsten carbide, and the thermocouple is no longer reading correct from there on.
That's a very good and valid point. It did read the same temperatures as it read well below in post-calibration, so maybe that mitigates the point, and I don't know. You know, I guess the outer thermocouple I don't have the data for the outer thermocouple. I think it is in the charts there, but I think that also would follow the expected regime beforehand, but that's as it is. Yeah.
Bob? Very nice presentation. I may have missed it. Is the hydrogen ordinary or isotopically pure?
It's ordinary hydrogen.
I have a question regarding the consumed fuel. So the conclusion was that the fuel was consumed at the end of that excess heat generation. Now, what was really consumed? There was nickel at the end still available. The hydrogen was refilled. What element was consumed?
So there's a many hypotheses. What we do know is that the calcium went from less than 1% to around about 20% in the inner heater tube, which we now, through forcing the situation and doing our own analysis, was actually silicon carbide. Like I say, he makes a point of saying that he could not see in the analysis of that inner tube that there was anything below aluminium, and we have been told that his previous reactor to that reactor contained boron, but yet we've actually got to confirm that. It may be boron, is what I'm saying, but whatever it is, it stopped producing excess heat.
Oh. Thank you very much. Very nice presentation. I'm very interested in your talk. I have a question about the calcium you detected. Did you measure the isotopic anomaly or something like that?
What I can say is I have some in here, and we can, but we have not yet.
Okay.
And in fact, they should have measured it at Synthestech. They may have that data, but it's not public. But we have some material here, now that we understand that calcium is important, to be able to potentially measure that.
Okay, good. Thank you.
I'll get to you, Peter.
Bob, I have two questions. First, what kind of nickel does it use?
It's on slide 3. You've
nickel.
even had about 4 grams of it. The same stuff we gave you in Padua. If I go back to the beginning, exactly the same stuff, PKN02, that I showed you the picture. How do I go to the beginning? You'll get there. I'm getting there slowly.
There. And second question is...
So it's carbonyl nickel, to answer your question, and it's a Russian-made carbonyl nickel.
The second question is, if you go to 800 1800 centigrade, it's all melted and
It
vaporized.
starts to center at 450 degrees. That's not the point.
So what
I guess.
happens at 800 degrees, 1800? What's happening at 1800 degrees?
Well, if there is boron in the reactor tube, nickel will interact with boron 1400 to 1600 degrees. And it may withdraw it out. But that was when I was looking at something that was not silicon carbide, so I haven't done...
But the nickel will be melted.
Yeah.
And then
And it was. You can see it's a big blob at the end. So I think you set up a scenario where something is made and it can do work, and it can do work preferentially at temperatures over 1100 degrees centigrade. Definitely not below 1000 degrees centigrade.
Okay.
So because the melting point of nickel is 1532.
Oh no, but it sinters because you look at the dendritic structure. Well, not the very fine peaks you've got here. That everything's not going to be at the bulk temperature. You're going to have extremely high temperatures on the tips, and that may be playing a role in setting up whatever is doing the work later down the line. And once it's in the system, the nickel really isn't playing that much of a role. But this is a hypothesis.
Oh,
Yes, Peter.
Just simple question. So did he measure only the thermal temperature? That's it. The measure is...
He measured radiation counts. I don't know if there's anything on there, but I don't think it was anything serious.
Yeah, because if you think about some kind of a heavy nuclear fusion, they should measure at least the gamma rays.
You would have thought so, but it would seem that there's been lead synthesized. Lead has been synthesized by Adamenko, and there was radiation concomitant with that, but unfortunately he synthesized radioactive elements at the same time, and lead was synthesized with Leclerc in a completely different system, but again, he got radiation because he was synthesizing transuranic, so these are not surprising. This is a gentle system, and so maybe in this system, with whatever is playing the role of doing the excess heat generation, it's not actually generating really heavy elements that then fission and produce radiation.
No, they have... the reaction should make a unstable nuclei.
Well, so the way Alexander Parkhomov explains it in his theory, which I will do in a poster session, the poster will hopefully be up by Wednesday, he's essentially saying that over 1,000 degrees in a metal and a liquid, not a gas. In a gas, the likelihood of this interaction is 7 orders of magnitude lower. So in a metal and a liquid, you have this massive potential of synthesis of ultra-low energy neutrinos. And they're formed in pairs, neutrino and neutrino, and these play a role in reverse beta electron processes. And you basically end up with synthesis of elements, either 2 to 1, 1 to 2, and 2 to 2, and that's a gross simplification of the process, because it is a correlated lump of atoms that all do stuff at the same time. But certainly the calculator that we have, which I will be able to take anyone's data through, is rudely good at predicting outcomes.
I'm interested in the hydrogen. So in previous experiments, the hydrogen started out as lithium aluminum hydride. Is that the same situation here? Okay, so I can speak to that because we had some experience in Bang. We had an explosion with our very first test. We put lithium aluminium hydride into that exact nickel, into a reactor. Actually, no, it wasn't. It was a different type of nickel. But anyway, it was a similar kind of structure, but slightly more filamentary. And when we looked at the aftermath of that, in fact, it was Ed Storms that looked at it, the lithium had covered these wonderful surfaces that have a potential to do some goodness. Subsequently, having done very many experiments that failed, Parkhomov concluded that the lithium actually stops the nickel from performing the process that actually creates the thing that does the work.
So how does the hydrogen get in? Is it gas?
He's got that, and he puts gas in. It's nickel and hydrogen, it's Piantelli.
And so you can, I mean, do you refresh the hydrogen or does
So in my talk and in the paper, he specifically notes that he tries to add hydrogen at 2 separate points in order to see if he can revive the excess heat. So what he's trying to do is find out whether it's the hydrogen that's important. But of course, at that stage, the nickel isn't in this state, it's more in the blob state. So he probably can't build more of the active structure that does the work because it hasn't got the facility to do it because it's not like that anymore.
Right. So in the Piantelli experiment, the hydrogen would be flowed through.
Well, he did pressure pulses, but Piantelli did shock pulses, he did laser pulses. Everything's in his valid patent till 2032. Piantelli, this is something that Piantelli hasn't disclosed, and I think it's important because it speaks to what Francesco Celani is doing, and where there is a lot of mistakes being made in this field, based on what works, what we've seen work, is that in his patent he has the platinum heater wire is much, much higher density at one end, and then it goes down to almost nothing. This creates a heat gradient, and he specifically showed us the nickel, and it's only a very specific point on that piece of nickel that gets hot, and then it moves along as the temperature goes up.
Okay, and so doesn't seem to be much different in excess heat production below melting point, above melting point of the nickel, or?
No, actually his theory specifically states, and his observations.
I was going to say, it's interesting the observation, not the...
Okay, so the observation is that nothing really happens, and there's a little effect below sort of 1,000 degrees, but basically, essentially, nothing happens until 1,000 degrees. And then as you go higher and higher, it gets very much bigger.
And finally, the pressure of the hydrogen?
The pressure of the hydrogen started off around atmospheric, it went to a bit above, then it went below, and it stayed at about 0.8, and then he repressurized it.
What was the size of the carbon?
The carbon.
It's a nanotube, or
I'm willing to share we have a lot more SEM imagery. They're very thin nanofibers that are really quite long. And then, well, if I go to the
because
structure,
might want to be good, to check the crystal structure. It might be a new polymorph of carbon, which would be very interesting.
It's absolutely mad what it is. I don't know what it is.
So it would worth to check.
So you can see here, this is actually, the large sticks you're seeing are the segments of the silicon dioxide wool that was used to separate all of the components, okay? And the fluffiness that you see here is this weird fluffy carbon, and here, this is you can see these fibers over here. And these are very similar to the fibers that were synthesized in Leclerc's reactor in terms of morphology.
Yeah, could you show me again the nickel slide?
With the isotopes?
No, the MEMP slide of the nickel, how it is. Because there is a white bar, which seems to indicate 20 micron length, right?
Sorry,
so
this slide?
Yeah, that one,
okay.
Yeah. The white bar is 20 micrometers length?
Yes.
All the white bar?
Yes.
Okay.
And so each one of those is 2 microns.
Okay, so...
subdivisions.
Okay, so as I have some background in catalysis, in organic chemistry, and especially using organometallic catalysts, it's well known that the deactivation of a catalyst may occur when the atoms forms cluster, and so there is a deactivation of the catalyst. So you are running with a catalytic reaction, and my question is, could it be possible to add something in this nickel, on this nickel, to avoid maybe the clustering of the material?
Maybe, yes.
Some nanoparticles or things like that?
Well, I think people have done that in the past by putting it in things like zeolites and stuff and looking at ways to separate the active structure. So imagine if you got some zeolite and you managed to get some water with these nickel particles in and you flowed it through, it would capture some of them and then they would be maybe enough separated. But I think when you're getting up to well beyond the melting point of nickel, it's really academic. You're always going to get it melting.
Alexander is an expert at radiologic measurement, gamma measurement.
Yeah.
Did he share any measurements during that very, very, very long experiment?
There is observation by Zhigulov of strange radiation, but there's some debate about whether that is there or not, and so that's something that we need to maybe address. But strange radiation may cause secondary radiation that looks like normal radiation that we understand and generally talk about. So apparently there was strange radiation observed from this reactor as well as the Woodpecker reactor.
So maybe just suggestion.
Sorry, so can I just do one follow-up point on that? Baranov and Zatalepin ceased working on powder reactors because they had a very large powder reactor, and they prepared it maybe in a similar way to as Parkhomov has described here, and they loaded it with fresh hydrogen, and at that point the entire lab filled with strange radiation. So they decided basically until we understand that, they're not going to look at it again.
What do you call strange radiation? I don't see that in my textbook.
Well, the only thing that's been really well studied is the work by Alexander Shishkin and the team of about 9 scientists at Dubna Science City. And they've observed these bird structures on X-rays, and this has also been observed at the Moscow Physics Laboratory by Bogdanovich using plasma discharges. And he concludes because they can carry nuclei of atoms out of something through metal, that it has to be a neutral structure, and it masks the charge and inertia. And then when it gets into an X-ray plate, they actually have seen and characterized pits, both the diameter of the pit and the depth of the pit, that's based on the atoms that have been captured by the string vortex soliton as it's traveled through a gas or a metal or something. So and they've actually well characterized. So if it goes through nitrogen with a factor, you see the depth and the width of the pit hit on the X-ray.
So, just suggestion. We use Constantan, nickel kappa. Inside specific glass sheet is a borosilicate, means boron calcium. So when after sometimes we make some X-ray analysis, and we found the nickel make like a alloy, so it changes everything. So
yeah,
maybe
so
you have to consider this point.
On the same point,
you can have segregation and so on. So
yeah.
the melting point can change just because local alloying.
Yeah, and I mean, the alloy can happen at a distance as well. So, as I was just saying with Mathieu, that you can get the transport of material to other places in the reactor. And for instance, I didn't show it here, but in the outer sheath, the very outer sheath, we have spheres of iron synthesized, maybe synthesized, but we've got spheres of iron inside the large spheres of iron inside the actual ceramic sheath.
Dear colleagues, I'm extremely sorry to interrupt the discussion, but we are asked to go for a coffee break, you see. So please enjoy your coffee break.
If anyone wants to ask any other questions or see the samples, they're welcome to.